Welcome back to this course of nanostructured materials, synthesis, properties, self assembly and applications. We are now in the module 3 and we are trying to understand the concept of self assembly and the applications that self assembled nanostructures can be used for. And in self assembly we have finished 2 lectures on self assembly, and now today we will have the third lecture on self assembly, and this is the lecture 9 of module 3. So, self assembly can be done at interfaces as shown in this figure here. If you have an interface between 2 different mediums. So, 2 different media means say you have liquid and solid. So, between the liquid and the solid you have an interface. So, can you self assemble, that means can you arrange nanoparticles or nanostructures at this interface. So, this interface if you bring around nanoparticles, can you arrange them in a particular fashion like this or in any other fashion, maybe in a square pattern or in a triangular pattern. So, that would be assembly at interfaces. Now, based on the how the interface is formed, what are the 2 different phases? One of the type of interface you can have is the liquid air interface. That means, you have one liquid, on top you have air. So, where the air is meeting the liquid, you have the air liquid interface. You can have self assembled structures made of nanoparticles at this interface. Then you can have 2 different liquids and the interface between 2 different liquids. This is possible when the 2 liquids coexist with each other, that means they do not dissolve in each other, and an example is like water and oil. So, water and oil do not mix. So, when you have a layer of water and a layer of oil, you will have an interface, and at that liquid liquid interface you can have assembly of particles. So, oil generally you can have many types of oil. In the laboratory you are used to chemicals like toluene, benzene, hexane. These are non-polar solvents, and these are like oil which do not dissolve in water. So, they are non-polar, water is polar, and between the non-polar liquid and the polar liquid there will be an interface. So, that will give rise to this liquid liquid interface. Then you can have a liquid in contact with a solid, and that will give you a liquid solid interface. So, that can be very easy. If you have say a silica surface and on top you have a drop of water, then it will create a interface between the liquid and solid. Now, there are some of the main techniques which are used today to make these kind of nanostructures or the assembly at the interfaces can be due by the well known Langmuir-Blodgett technique. We will discuss this in detail. Then you can have sedimentation or evaporation induced self assembly. Then you can have adsorption of nanoparticles on a surface. So, there are different types of techniques one can use to make ordered assemblies of nanoparticles at interfaces. So, first let us discuss the liquid air interface. So, by the name you can understand that you have a liquid on top of which you have air. So, you have an assembly on the surface of the liquid, there is a contact between molecules of air and the molecules of the liquid. Now, at that interface how to make assembled nanostructures. The technique that commonly people use to make nanostructures at the liquid air interface is using the Langmuir-Blodgett technique, and it is more or less it is called programmed self assembly. You utilize the solvent or the liquid in most cases is water in the LB technique or the Langmuir-Blodgett technique. So, you are basically looking at the water air interface, and there the hydrophobic and hydrophilic properties of the molecules are very important for this kind of technique. So, hydrophobic and hydrophilic, for example, you have water. So, you will have hydrophilic interactions, and if you have a surface which is, for example, you can have a silica surface which is hydrophilic, and you can change the hydrophilic silica surface by using a silane, say alkyl silane, and you can make it hydrophobic. So, these interactions between hydrophobic surfaces with hydrophilic or hydrophobic molecules is important for making nanostructures using the LB technique. The surface tension of water plays a crucial role in this technique, since water is the key liquid being used in Langmuir-Blodgett technique, and hence the surface tension of water will be very important. So, let us understand what is this LB film or the Langmuir-Blodgett film. So, it contains one or more monolayers of the material. So, a film made at the liquid air interface of some nanoparticles on the liquid which is water on the water surface, that is basically a Langmuir-Blodgett film, and this process, as we have discussed, is made at the air water interface. So, this is the photograph of a LB trough. So, this is called an LB trough. It is made normally of Teflon, and you have water inside, on top of which you want to make the film, and on either side of this trough you see these kind of Teflon rods, square rods. So, they create a pressure on the film. So, they are called barriers, and so this one moves inwards and this one also moves inwards, creates a pressure on the surface of the fluid here, and the fluid here is water, and if there are molecules on top of water, you can dip a substrate on the inside the liquid and pull it out, and the molecules on top of this water will make a film on the substrate which can be dipped from the top. So, this can be controlled through a computer. The rate at which the barriers move, the rate at which you dip the substrate, etcetera, can be controlled. So, this is basically the LB trough it is called, and the process which occurs is that you are moving this barrier, which are there 1 and 2 barriers. So, they are here on 2 extremes, and you are pulling this barrier inside from both directions, and the water has got these molecules on top of it. So, when you are creating a pressure and you are dipping the substrate from the top or pulling it out, here the arrow is showing that you are pulling out the substrate. So, the substrate is here, which was dipped in the liquid and is being pulled out. So, when you do that, then the molecules on the liquid, on the top of the liquid, the molecules on top of the liquid come on top of the substrate. So, typically if you have a substrate which is hydrophilic, then the hydrophilic part of this molecule will be adhered towards this substrate or adhered on the substrate. And so, depending on what kind of film you want, whether you want the hydrophobic part sticking out or the hydrophilic part sticking out, you have to take the surface of the substrate accordingly. So, this is the basic process. You are pushing from both sides the barriers which are at these two extremes and creating a pressure on the film of water, and the film of water has got these molecules on top of them, which will get coated onto the substrate, and that will form the monolayer. So, one layer of the molecules are now coated on the substrate when you take out the substrate. So, this is again showing you now different types of molecular assembly which you can achieve using the LB technique. So, here in the first case you see there is water and you have your substrate and you are pulling out the substrate. The substrate is chosen such that you want the film to be on a particular substrate, and you choose the substrate accordingly. So, you put in pressure from either side. So, the two barriers are moving in and one monolayer is forming at the water and air interface. So, on top you have air, below you have water, and you are having a monolayer or an assembly of molecules at the air water interface. Now, instead of pulling it out, you can pull it in. So, this is an LB deposition on a hydrophilic surface. Now, you can do LB deposition on a hydrophilic surface for the second layer. So, this is first layer is formed. Now, you want to make the second layer. So, after the first layer is formed, so the substrate has come up. Now, you push it back. So, this is showing when you push it back, then on top of the first layer a second layer will start forming, and you see the two hydrophobic parts are close to each other. So, when you push in the substrate, the second layer of molecules on top of the water layer will form the second layer, and ultimately you will get a substrate which has got two layers. So, it is a bilayer on top of the substrate. On a hydrophobic surface, if you do the same thing which you did here, you pulled out the substrate, it was a hydrophilic surface. When you have a hydrophobic surface, you push in the substrate and you have an LB film with the tails on top of the hydrophobic surface. So, depends on what kind of substrate you have, whether hydrophilic or hydrophobic. Then the first monolayer, either you will have to pull out the substrate or push in the substrate, depending on what kind of substrate you have, whether it is hydrophilic or hydrophobic. Now, you can have multiple layers, and there are different classifications of these LB films. For example, this is showing a 3-layered LB film, and it is called the Z type, because all the molecules are pointing in the same direction. So, you have one layer with the head group pointing in towards the surface of the substrate, then the second layer is again pointing towards the surface of the substrate, the third layer is also pointing in this direction. This is the opposite type, where the tails are close to the substrate, and this is on a hydrophobic surface, and this is an X type on a hydrophobic surface. Okay. So, if you have alternate, that is one pointing in this way, the second pointing that way, the third one again in the reverse direction, then that is called a Y type of a molecular assembly or a Y type of LB film. So, you have different types of LB films, and this is precisely the process by which you make the Langmuir-Blodgett films on substrates. So, what are the interactions when you are making the film? So, this is the trough which we discussed. So, this trough contains water, and also it contains the molecules which are spread out on the surface of water, and you want to make an LB film using these molecules on a substrate. Now, the two barriers are shown here, this is one barrier and this is another barrier, and you have to push the two barriers close to each other when you are dipping the substrate to make the film. Now, you can have different types of molecular arrangements when you are making the film. So, as you are bringing the barriers are at a distance. So, the average area per molecule is very large when the two barriers are far off. So, when the two barriers are very far off, then the number of molecules per unit area is less. So, the number of molecules per unit area is very less when the two barriers are very far apart, and the surface pressure when the barriers are very far apart is very less. When you are bringing the two barriers closer, the number of molecules per the average area per molecule, you can say, is becoming lesser and lesser as you are bringing the barriers close to each other. So, then the surface pressure rises. So, the surface pressure rises, and as you bring it further down, it again rises, and this whole plot of the change in surface pressure with decreasing distance of the barrier layers, or you can say decreasing distance, decreasing average area available to one molecule. If you lower that, the surface area, the surface pressure is increasing, and there are certain stages. As you can see, the slope of the curve changes at this point, and then again changes at this point, and then there is a further change here. So, this region till you come to the first point is called the gaseous two dimensional phase, when the molecules on the surface of water are totally disordered. That is called the gaseous two dimensional phase. When the area available to the molecule decreases, the molecules start getting arranged in a particular fashion, and that is the expanded two dimensional phase, or it is called the liquid like phase, liquid like two dimensional phase. On further closing down the gap between the two barriers, you are forcing the molecules to arrange in a definite pattern, and that is called the solid like two dimensional phase or the condensed two dimensional phase. If you bring the barriers further close, the pressure will increase drastically, and at a particular point the film, which was very well structured like a solid like regular pattern, will collapse, and you will have breakdown of the film, Langmuir-Blodgett film. So, you have different sections of this plot, the gaseous 2D phase, the liquid like 2D phase, the condensed 2D phase, and then the collapsed film at very high surface pressure, that is when the barrier distance, the distance between the two barriers is very low. This is can be shown on top of the surface, it will appear like this when it is very well ordered. So, the films will look like this, where the blue balls are basically the hydrophilic or the polar head groups, and these are the carbon chains or the hydrophobic tail, which are pointing outside the aqueous layer. Now, the same plot which we called a Langmuir-Blodgett isotherm, where you plot the surface pressure with the area available to each molecule on the surface. So, this in a simplified form for lecithin, which is a molecule like this, it has a head group which is this trialkyl ammonium head group, and then this hydrophobic chains. So, you have the 2D gaseous phase. So, if you have lecithin molecules on water and you are applying barrier pressure, that means bringing the barriers close together, then you first go from the 2D gaseous phase to 2D liquid like phase, then the 2D condensed phase, and then at this point you see the there is a breakdown, the pressure no more increases, because the ordered 2D phase has collapsed and the Langmuir-Blodgett film has broken down. So, this is an example of an LB isotherm. These are experimental data. So, these are TEM images of LB films, and you can see these are mixed octadecylamine. Octadecylamine will have large this chains, octadecyl chains, this 18 carbon chains, and you have gold nanoparticle, they form monolayers at various surface pressures. So, you can see that you have low pressure 17.5 millinewtons per meter applied here, and the film is not continuous. As you are increasing the pressure, the film is becoming more homogeneous, more continuous, and at 25 nanometers it appears to be exactly homogeneous. Again, if you overshoot this pressure in this particular case, say you go to 30 millinewtons per meter, you start the breakdown of the film, and now you see these holes within the film. So, after 25 millinewton per meter, you have basically reached the collapsed form stage of as shown in the LB isotherm. So, in this LB isotherm, at a particular pressure, for lecithin this is like 200 centimeter square, where the pressure is something like 40, maybe 40 or 42 millinewtons per meter, and if you are around that, then the lecithin film breaks down. In this particular case of octadecylamine gold nanoparticle monolayers, the pressure at which the film breaks down is around 25 to 26 millinewton per meter, and this is another picture of LB films. So, you can see very nice assembly of silica spheres made by LB method, and you can see a very compact self assembly of nanoparticles. So, at different barrier distances, so if you look at the barrier, again let me show you the picture. This is the real LB trough. The barriers are here at the two extremes, and when you are bringing them together, the pressure will increase, and this is shown more schematically. The barriers, when they move towards each other, lower the area available to the molecules on the surface, and then the molecules start organizing or assembling into regular patterns. Of course, once it forms a complete film, if you put extra pressure, that means if you bring the barriers closer to each other, then the film will disrupt. And so, that is the example that we did of octadecylamine with gold nanoparticle monolayers, and this was silica spheres making an LB film and forming an assembly of nanoparticles. Now, that was air water interface, that is liquid and air interface. So, that was one kind of interface, how to make self assembled structures at the air liquid interface. We can also have liquid liquid interface. So, two liquids, and then how we can absorb nanoparticles at that interface to form assembly of nanoparticles. So, in this case, the free energy of the system reduces. The reduction in the total free energy system is important for the adsorption. So, whenever adsorption occurs at this interface, it should lower the free energy of the system. So, let us consider an oil water interface, and this delta E is the surface energy reduction, which will contribute to the lowering of the free energy. So, this surface energy reduction is given by these terms, where these gammas are basically the surface tension of the oil water interface, the particle water and the particle oil. So, you have different gammas depending on the material you have, which oil you have and which nanoparticle you are using. You will have different numbers for these, and you can calculate for a particle of size of radius a, what would be the reduction in the surface energy based on this equation, and that will give rise to a reduction in the free energy, which will lead to the adsorption of the nanoparticles at the liquid liquid interface. So, for an example, this equation, if you take these numbers, for example, you take the surface tension between the oil and water to be 35.7 millinewton per meter, and similarly you take the particle the oil interface to have a surface tension of 15 millinewton per meter and the particle water to have 40 millinewton per meter, then the change or the reduction in the surface energy is about minus 5 k T. So, this k B here is the Boltzmann constant, and so it is about minus 5 k T if the diameter of this particle, here A is of course radius. So, if the radius is 1.4 nanometers, that is for 2.8 nanometer diameter particles, this value comes to around minus 5 kBT, and it is to be noted that E here, the reduction in energy delta E, is directly proportional to the square of the radius. So, the energy gain is smaller and the assembly is less stable for smaller nanoparticles, because it depends on the square of the radius. So, and it is negative. So, if it is the particle size is very small, then the monolayer that you get, the LV film, you get the self assembled layer which you get on the liquid liquid interface is much less stable than for particles which have a larger radii, and that is given by this equation. So, this is an example of self assembly of colloidal nanoparticles at a fluid fluid or liquid liquid interface. So, the two liquids here are toluene and water. Toluene is an organic solvent, it is non-polar, water is polar, and they are not miscible, and so when two liquids which are immiscible meet, they make an interface. And what happens if you add some cadmium selenide nanoparticles? These cadmium selenide nanoparticles will form an assembly at the toluene water interface. So, if you see these circles, so more clear here, if you see these circles, you can see that green emission is coming from the 525 nanometer emission from the cadmium selenide nanoparticles, which are at the interface of the toluene and water. So, the water is outside and toluene is inside, and at the interface the cadmium selenide nanoparticles will arrange themselves. So, if you excite them with this 488 nanometer laser, then you can see a green emission which comes at 525 nanometer. This green emission is coming from only this interface area. If you take a depth profiling, that means this is looking at the same droplet, but in the z direction. So, you are going down in the z direction, you see that when you are going at inside the particle. So, it is at the top surface, you see something, then you this is the particle is becoming larger, because you are now at the center of the particle. So, the cross section is larger, again you are going down further, the cross section becomes smaller and smaller, and when you go into the center of the particle, there is no emission, because the emission is all at the periphery, and so that suggests, that tells you that the cadmium selenide has not gone inside the liquid particle, but it is at the interface. So, this is a confirmation by confocal fluorescence imaging using studying the fluorescence coming out from different depths of the same particle, of the same interface, and that tells you the self assembly has taken place at the interface. Now, you can come to the example of solid liquid interface. So, we looked at liquid air interface, we looked at liquid liquid interface, and then now we want to look at liquid solid interface. So, in liquid solid interface you can prepare an assembly of particles by the evaporation mediated method. So, here the key step or the most important step is how you evaporate the solvent on top of the solid liquid interface and what is left behind on the solid substrate. So, this process can however be assisted by electrostatic interactions, van der Waals forces and dipolar interactions. And it is very important because this methodology of making assembly on solids is very useful going by the liquid solid interface route, because you can make large area structures. So, you can take a large solid surface and you can slowly evaporate the liquid and create a self assembled assembly of nanoparticles on the surface of the solid, and you can use them for applications. And examples of semiconductors, metal, magnetic nanoparticles have all been demonstrated in the recent past using evaporation mediated method on the liquid solid interface. So, this is an example of a liquid solid interface. It is a classic paper on published in Nature in 2006, where people have used evaporation mediated method to form patterns. So, you see these are patterns of colloidal particles lead selenide on silver